Hi, my name is Jake Kupman, and this is my presentation on the traveling salesman problem and some algorithms that we can use to approximate solutions. The first, what is this? So the problem is that we want to determine the most efficient way to complete a certain number of tasks. So in graph theory, this can be stated as the shortest or least weight cycle that visits each vertex once and only once. This problem is both very common and very complex. So some practical applications. First, a traveling salesman, as the name implies. The salesman has multiple different towns or cities that he needs to visit. It's often desired to do this in the most efficient manner possible so that he can finish his route as quickly as possible. Then hole punching in the manufacturing context, specifically with the automotive and electronics industries. They take boards or metal plates and they punch holes in them to create their products. So it's often desired that they do this in the most efficient manner possible. And then with job sequencing, if a machine has multiple different tasks that it needs to complete, often the problem is figuring out the most efficient order to do these tasks, minimize turnover time. There's some specifics of the problem. We have a graph where V is a set of n vertices, A is a set of arcs or edges, and then let C be a distance or cost matrix associated with these arcs or edges. C is said to satisfy the triangle inequality, which basically states that the distance between two vertices, I and K, is equal to or less than the distance from I to J and then from J to K. Um, Pretty much saying the distance between two vertices is shortest if you go directly between them. So the goal of this problem is to determine the minimum distance or cost circuit that passes through each vertex once and only once. This problem is pretty complex. At first, when we have a small number of vertices, the problem is pretty quick to solve. Yeah. If we have four vertices, and we're calculating every path possible starting from one vertice or one vertex. Um, we can calculate the cost of the six different paths pretty quickly and then kind of determine which one's the most efficient path. But when n is large, the problem is pretty difficult, um, sometimes even impossible. If we just bump n up to five, then we can calculate 24 different paths. And so just one increase in the number of vertices increase the number of paths by 18. This problem is also NP hard. When a problem is NP, it means that it cannot be solved in polynomial time, but that a solution can be checked in polynomial time. So NP hard problems are at least as hard as the most difficult NP problems. So they don't always have a perfect solution, and they're often not checkable quickly. So how do we solve this problem? We have both exact algorithms and heuristic algorithms, which are like approximations. Um, so first, some exact algorithms. First, the brute force algorithm, just similar to what we did in a few slides for this one, where we just calculated every single path possible, and then determined the most efficient path from calculating every path. Then there's also Danzig, Fulkerson, and Johnson algorithm, and the Miller-Tucker and Zimlin algorithm. Some heuristic algorithms. First, what is a heuristic algorithm? It's an approximation that seeks a good enough solution with the use of shortcuts and educated guesses. Aho, Hopcroft, and Ullman discovered that this can be done in polynomial time by traversing a spanning tree along its edges. Christofides built upon this algorithm and actually made improvements to it. So we're going to look at both of those algorithms. So first, Aho, Hopcroft, and Ullman, AHU. So we're going to consider any leaf or a vertex of degree 1 in the spanning tree and set that equal to I. So for this example, we'll take vertex 1. If there's any untraversed edge connected to the vertex 1, follow that edge to vertex j, and then we're going to set j equal to I. So our first move from vertex 1 would be to vertex 3, which would then become I, and then we could move to vertex 2 or 4. So we're going to repeat step 2 until all the edges have been used. And then we're going to return back to our starting leaf, which was vertex 1. Christofides algorithm. So the first step is to find a minimum spanning tree of the graph, which is shown on the left graph. And that's pretty much just a tree, meaning that all the vertices are connected. There are no cycles present. And we're going to use the minimum weight edges that we possibly can. Then we're going to determine which vertices have odd degree. So that would be, in this case, vertex 1, 2, 3, 5, 7, 8, and 6. And so then we're going to find a minimum weight perfect matching of these odd vertices. And so essentially there we're just going to connect all of our odd vertices together um, in pairs of two to make them even vertices. But we're going to do this using the minimum weight edges, the most efficient edges possible. And then we're going to combine the MST and the NPM. And then once we've combined these, we're going to find a Eulerian cycle. And then we're going to shortcut this cycle by removing the vertices that we've already visited um, prior to visiting them again. So when we compare these two algorithms, um, we can see which one is more effective. Um, so when we shortcut the AHU, it produces the path 1, 3, 2, 4, 5, 6, 8, 7, 1. And then when we shortcut Christoph's algorithm, it produces the path 1, 2, 3, 4, 5, 6, 8, 7, 1. And so both of these have the same number of edges, which may lead you to believe that they are both the same distance, just as efficient. But we can see if we look at which vertexes we're traveling between, that the distances in Christoph's algorithm are much shorter, much more efficient. So the accuracy of this algorithm, um, Christoph's algorithm is a 3-to-2 approximation algorithm, which means that at worst, this algorithm produces a path that is 1.5 times longer or more expensive than the optimal path, which may seem like a bad approximation. But it's important to note and remember that 1.2 times the optimal solution is the upper bound. And so the solution is often much closer to the optimal solution than the upper bound makes it seem. So in conclusion, this problem is very common and therefore very important. It can be found in things as common as planning routes for errands or something as complex as hole punching. While this problem is very common and is very complex, and thanks to the development of algorithms like Christoph's, graphs including hundreds or even thousands of vertices can be solved in a relatively timely manner. And here are my sources. Thank you.